This here. All right. So, okay, so we're shifting right. So now, if we are shifting to the right, that means we're making more of this. Well, how do you make product? Well, you have to use up your reactants, right? So I have these up here to kind of help us understand that. So, in Silas, this is what I was talking to you about yesterday. So I'm going to take, let's say I have 4 of each of these. Okay. All right. And let's say I have 4 of these. 2, 3, 4. Okay. Actually, I'll do it this way. Okay. Just bear with me here for a second. All right. All right. So these only react in a ratio of 1 to 3. So in other words, 4 of these can never react with 4 of these. That's impossible because the balanced equation says 1 of these reacts with 3 of these. And then when that happens, you make 2 of these. So I know it's 1, 3, and 2. What I'm showing here is not supposed to match that. All right? This is just how they actually react. You can have way more in a container than how much actually reacts. That's what the reaction tells me. Doesn't mean I can't have more of them. So don't get confused with comparing the numbers up here to what you see here. That's not what I'm trying to do. What I'm trying to do is explain the increase-decrease stuff. So if we add H2, that's like adding more of the blue ones. So if I add more of the blue one, let's say I add 1 more blue one, okay? So if I add more blue, right, add the H2, now this side's too heavy. So what has to happen is I need to make more products to try and balance that out, to give it back to equilibrium. So what happens is I need to take 3 of these, and I need to take 1 of these to make another ammonia, and actually that's not going to work, so now we have to do that. And now, as a result, when I add more hydrogen, not only does the hydrogen decrease, because I need to use it, but the nitrogen decreases as well, right? So I add hydrogen. Temporarily, this goes like this, temporarily. Now they actually react together, make NH3. Why? Because now this side needs to be heavier. And again, I'm using heavy and light. That's not how it works, but it's just for the analogy. So now we know, okay, we're shifting right. I think everyone gets that. How does it affect the N2? We just saw it decreased. I had to break it up to make more NH3. So the N2 decreases. Well, you just saw I added 2 NH3s, so my NH3 increases. So I'm trying to do a couple things here. Use this to help you see it and understand. Maybe this helps some of you, that if I start piling more over here, that means I'm making more. It's increasing. If I'm taking them away, that means they're decreasing in concentration. So this morning when I was all done with class, I asked them, was this helpful? Most of them said this is more helpful, which is fine, but a couple of them said this is, this helped them. So hopefully it's helping. Something I'm doing here is helping, hopefully. Because after I go over this entire worksheet, we'll finish this tomorrow and Thursday. That's it. I don't give you any more notes. I kind of use this and teach it slowly to learn, to help you learn. All right, here we go. Now, add NH3. All right, Tyler, which way are we shifting if we add NH3?
Shift. It's like you're
So, all right, yeah, 2-step process. If we add NH3, how does this get all screwed up?
going like go down to the right.
Right, so now how does it shift to go back to equilibrium?
Shift left.
Shifts left. So for number 3, adding NH3, it will shift towards the reactants. Good. So now it's the opposite of what we just did. I have to take these apart because I just added more NH3. So I have to take these apart and I have to make more hydrogen and more nitrogen to balance it back out. So it's the exact opposite of the other one. If I pile on NH3, it's actually going to use what you just added and make more reactants to go back to being balanced. So these two will both increase. So for number 3, we're shifting left. N2 and H2 both increase because I just had to take that apart to shift to the left. I had to make more reactants. All right, number 4. Caitlin, what do you think? First, tell me, how does this change if I remove N2? Try again. Yeah, because if I take N2, if I take some of this off, right, if I do this, take these away, so now this side's going to be too light. So which way does it shift? To the left, good. So we're shifting left because we just removed N2. So what the equilibrium does is it shifts to fill in what you just took. So we're shifting left, so now these two might break apart, and now we have these two, and then there we go. So again, the numbers of like two of those, that's not what I'm trying to worry about here. I'm just showing you, if we're shifting left, I'm taking these apart and I'm gonna make more reactants. So for number 4, we're shifting left, H2 increase, we added a whole bunch of those, and NH3 decrease. I had to use NH3 to make N2 and H2. So for number 4, we're shifting left, H2 is increasing, NH3 is decreasing. Number 5 is the exact same thing, except this time in number 5, I'm removing H2, taking a bunch of these out. So now I'm taking H2, so it's like this. I took some H2 off, so now we're shifting left again. These are going to have to break apart, and they're going to have to make more of what I just removed. So I'm going to take this, take this, put these together. All right, so now I don't have any ammonia. Again, that's kind of impossible,
That's
but
unbalanced.
yes, it is. But the point is, if I remove reactants, my products naturally break apart, make more reactants because I just took them away, and now that means these increase in concentration and that decreases. So for number 5, we're shifting left, N2 increase, NH3 decrease, and in this example, I don't even have any left, which again is impossible. But all right, and now let me go back. I gotta make some more for this one here. Let me put 2 of these. All right, so we'll do these. This is our starting. So let's say we're back to being balanced. All right, if I take some NH3 out, take this out, NH3 is gone. All right. What happens here? If I take NH3 off, think of a seesaw.
So the right would go down?
This, imagine you're sitting on here and I push you off.
Then it would go to the left.
What's going to happen to this? What's going to happen to the seat you were sitting on? A seesaw. It's going to go up. Good.
Yeah.
So that's what happened. We take. You know what? I was thinking of it backwards, maybe the way you said it. Sorry, because I'm standing on this side. So if we take this off, remove it, decrease concentration, whatever makes sense to you guys. This side goes up. All right, you get that. How's it shift? Go back to being balanced.
It shifts to the right.
Good. It shifts to the right. So number 6, we're shifting right. How do we shift to the right? We have to make more NH3. So when we make more NH3, Renee, what happens to the amount of these two?
It decreased.
Decrease. I have to use them. That's like the fuel to make this. I have to use them to make those, right? So if we're shifting right, this will increase, these two decrease. So the answer to 6 is shifting right, decrease, decrease. Questions on 1 through 6?
I just have a question on
Yeah.
this in general.
Yeah.
So I understand that this does happen, but I don't understand why, like why it reaches equilibrium and they go
So,
back and forth.
That has to do with K values.
Oh, okay.
Because, yeah, it's not super easy to answer. Let me try and do the best I can here. So, a lot of reactions just naturally progress backwards in reverse, and it has a lot to do with this thing called thermodynamics and Gibbs free energy and entropy, and there's a lot of there's like equations you learn in AP Chem that sort of explain this stuff. But you're saying why? So why does it even? How come they all don't just make NH3 and that's it, right? Why does NH3 ever go back? Because for some reason, and there's ways to figure it out, what it's called, it's thermodynamically favorable for that to do that. In other words, chemicals sometimes are more stable depending on the reaction and depending on which way they go, whether they're synthesizing or they're decomposing. So there is a driving force, and I don't know what it is off the top of my head, but that could cause that. So then just assuming that is what it is, when it settles out and all the dust settles, a better way to say it, you have 2 moles of this, 3 moles of that, and 1 mole of that. So when that is achieved, then this starts happening. So I didn't really answer it very well because it's not that easy to answer. But the best way I can explain it is that naturally these chemicals want to do this on their own because there's a driving force, and usually that has to do with thermodynamics, which deals with energy.
Okay.
So that's the best I can give you right now. Yeah.
So they're trying to become more stable?
Yeah, so in general, most processes in nature or in lab, if you see something happen, the chemicals are doing that because it's a more stable configuration. It's a favorable thing,
Then why does it become NH3 in the first place?
because that's favorable too.
So like both equally appealing. So they're like going back to see.
Well,
which they
no,
like
one of
more.
them is more equally appealing. So NH3 is more stable. This is more appealing than those two.
Okay.
So even when this thing reaches equilibrium,
Mhm.
it still favors the production of ammonia.
Okay.
And that's what the K value tells us. And that's what's hard to explain without, you have to kind of learn a whole bunch of stuff. So you can remember equilibrium means constant, not necessarily equal. So there's always going to be more of these than those, even though it says 4 to 2. It's really hard for me to answer. Like I have it in my head, but I don't know how to get it to you without
Teaching me all
taking
other
AP
stuff.
Chem, right? So yeah, that's a good question. All right, moving on. Any other questions with this, or any other questions you want to stump me with? Okay, flip it. I'm gonna go through the back kind of slow. The top chart, the bottom one, I'm just gonna read the answers because we gotta get rolling here. All right, here we go. So I'm not gonna do this anymore. I will use this, but that was just for that example. All right, here we go. So on the back, everybody with me? Jake, with me? Okay, good. Corey? All right. Alex isn't here. I just realized that. All right, here we go. Now, add I2. Fred, how are we doing? Some of this making any kind of sense?
Yeah.
Good. Tyler, so we add I2. Which way does it shift? What did you write as your answer? Good, shifts to the right. I's up here. Imagine H2 and I2 are sitting here and HI is sitting here. If I pile a whole bunch of I2, right? Yeah, I2, we're going to be heavier, so we got to shift to the right to go back to being balanced. If we're shifting right, we are making more HI, because that's what's over here. You shift towards it, you're going to make more of it. So HI increases, and then the H2, so the second box, decreases. You're going to use up your reactant to make more product. Another way to say this very simply, whatever you shift towards, you make more of. Whatever you shift away from, you have less of. Okay. 3, HI, we're adding HI. Becky, what do you think?
Left.
Yes, shifting left, eyes up here. We're adding HI, this side's heavy, so we shift left to go back to being balanced. If we are shifting left, that means H2 and I2 both increase because they're over here. We're shifting that way, we're making more of it. That's what I was trying to show here. When I take all of these and put them over there, you're making more. Remove H2, Shane, what do you think? Remove H2, just tell me the shift.
Left.
Left, very good. Again, eyes up here. I take H2, imagine H2 sitting on our seesaw. Psh, knock them off. Goes up. Now we have to shift this way to go back to being balanced. So we're shifting left. That means we're making more I2 and we're using up HI, so it decreases. So I2 increase, HI decrease. All right, remove I2 is the exact same thing as number 4. So you're just kicking off the other reactant. So the same thing, we're shifting left, H2 will increase, HI will decrease. 6, Will, what do you think?
Shifts right.
Good. Again, eyes up here, stay with me. Even if you got this, right? Stay with me, pay attention, look at me. So, HI, we're taking HI off. This side goes up. So we're shifting right to go back to being balanced. So, we're shifting right, HI is gonna, H2 and I2 are gonna decrease, right? We're gonna use these up to make more HI. So H2 and I2 decrease for number 6, because you're making more HI, because you just removed it. Questions on that top part? Bottom. I'm just gonna read the answers, here we go. Add NaOH. We are, and you know what? I'm just gonna do the shifting. I'm gonna skip the other part. Sorry you had to do it, but I'm gonna skip it because I'm not that worried about that right now. Add NaOH. We're shifting right. Number 2, we're adding Na+. We're shifting left. Number 3, adding OH minus. Shift left. And number 4, we're removing OH minus, which means we shift right. All right, now, before you put it away, due tomorrow, number 7 and 8, the temperature one's on the front, the temperature one's on the back, 7, 8, and then 5 and 6, the temperature one's on the bottom there. So just those 6 are due tomorrow, the temperature ones.
So all temperature
Just
ones?
all the temperature ones, yep. Take out your notes, please.
Wait, let me have this.
That's due Monday. Graded test, quiz, whatever you want to call it. Yeah, at this point, the rest of the year, you will always have multiple things going on for me.
Great.
You're welcome.
Thanks, I really like that.
All right. So here's what we're gonna do. We're gonna do 2, 3 practice problems to learn temperature. Yes, sir. You can, but hustle up. I want to make sure you get this. All right. So you need table I as well. So temperature changes affect the delta H. Delta H is the energy lost or gained. Table I tells us that. So I'm going to write a reaction on the board. You're going to look it up on table I. You're going to tell me if it's endo or exo. Then we're going to figure out as a class which side of the arrow to put it on. And then I'm going to give you a sample problem, and that's how I teach this. I'm not going to give you notes. I just think doing practice problems and discussing how to do it is more helpful. All right. Let's see. I'll write the reaction. You just find it. Here we go. Let's go. I like this one. For some reason, I just like it. All the numbers seem nice and neat. So find that. Figure out in your head, is it endo or exo? And then tell me, again in your head, which side do we put that number, right? So you look up the reaction, find the number, and say, oh, that's endo, or oh, that's exo. Now which side do you write it on?
Yep.
You too. Day late, dollar short.
Huh?
What does that have to do with French cheese?
Yeah.
It's the price of eggs.
Oh, what it has to do with the price of tea in China.
That too.
You do eggs.
Eggs. What has to do with the price of eggs?
No. We're just
I mean, really, you could say anything you want. What's it have to do with the price of a Lexus? I wouldn't buy a Lexus though.
I was thinking the name, like.
Yeah, like a person.
Seriously,
Yeah.
yeah.
Okay,
I was
fine,
like,
yeah.
why you
BMW or an Audi.
big Mexican
That's how I remember the plot.
You like BMWs, right?
Hmm?
So you like big Mexican women?
That's weird.
I'll take my joke.
And inappropriate somewhere in there. It's gotta be inappropriate. All right. Push go. All right. Who's got it? Obviously not these two.
Not yet. I'm working on it.
I got it.
Go ahead. Who's got it?
Oh, it's wrong? I got it.
Hold on, Jake. Tell me why it's endo.
He said exo. So
I know. So he knows he's wrong because I said that part. Look at the bottom of the chart on the left side. Or maybe you looked at the wrong reaction.
I did.
Yeah, that happens all the time. So there's two of them that look similar. This one, 202, 2NO2 is positive 66.4. All right. The one above it
It's positive 180.
is also positive. Sorry, Jake. Trying to bail you out there, but. All right. So now, Jake, redemption. It's endothermic. Which side do we put the 66.4 on?
What?
Sorry, I was writing down endo.
It's alright. So we know it's endothermic. Which side do we put that 66.4?
On the left.
Very good. Endo, we enter in the beginning. Endothermic. It needs that energy or else it can't react. It's another way to think of it. Exo at the end, exit at the end. Alright, so we know it's endothermic. Alright, now, actually I'm going to give you just one line of notes, then the question. We treat delta H / the energy as if it is a substance. Parentheses, reactant or product. So we are treating that 66.4 as if it's a reactant. If it happens to be on the product side, we treat it as a product. That's really important to remember, otherwise you can't really do these. Alright, again, this is Le Chatelier's principle. Concentration change is the first thing we learned. That was what the homework was on. That's if you add or remove reactants to products. Now we're going to increase or decrease temp. So, you treat delta H, the energy, as if it is a substance, reactant, or a product. So, why not put this back? I don't know. We act like 66.4 is sitting right here. So now we can add more of it, or we can take it away. Okay. I guess I'm going to give you one more line. Sorry, then the question. Increasing temp means equals increasing the energy. Or if we want to explain it a different way, adding more energy. Maybe that'll help some of you. Add more energy. Decreasing temp is the opposite. I just don't feel like writing that. I'm sorry. You guys, I think, can handle that. It's the opposite.
Isn't like temp always gonna like determine the amount of energy?
It's the other way around. The amount of energy determines temperature. Temperature just measures. Kind of like this doesn't determine the length of something.
Right.
This measures the length of something. So like the desk has to be a certain length before I use this.
Mhm.
Temperature is the same way. Temperature measures energy, kinetic energy. I'm teaching it a little bit kind of like backwards, but and it's not just me. All chemistry teachers do this because it just helps you understand the concept better. So these are related. Higher temperature, higher energy. Lower temp, lower energy, that's true. I think we all get that. Okay, so here's the energy. Here's the question, and I'm going to write it down. If I increase the temperature on this system at equilibrium, in which direction will it shift? So we're going to write that down and we're going to answer it. So here's the question. So we're using this reaction based on what we just learned. Here's the question. If the temperature is increased on this reaction, and the reagents will say on this reaction at equilibrium. They have to say that, otherwise it kind of throws the whole thing. You can't really ask the question. I'm not going to write that part. If the temperature is increased on this reaction, which is at equilibrium, in which direction will the equilibrium shift? So if you read those two lines, the two notes there, 2 lines of notes I just went over, that's how you answer this question. So, I did the first part for you. I had you look it up and then I helped you figure it out. But if this was a quiz or a test or Regents, they might just give you the reaction. You have to look it up, find 66.4, you have to know it's over here. That's half the battle. Now you can answer the question. So go ahead, take a minute. You got a 50-50 chance of just guessing, but I want you to figure it out. So we're increasing the temp, which means adding more energy. In what direction or which direction will the equilibrium shift? Get your Spanish done, Jane?
I'm gonna finish translating it during gym.
That's better.
I have one more.
Or I have a better idea. Just get it done before you come to school.
Not the
Do it that
it's
night.
just
Or study hall or lunch.
I had
All right.
another
Or actually, Corey, I'm not sure how much I called on you today. So what's the answer? Right. Very good. Everyone right. Right. Or arrow to the right.
Right.
It shifts to the right.
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 Now, Look up here. If 66.4 is sitting right here, it's one of the reactants, and we increase the temp, what that really means is making that number bigger. Make up a number, 100. Let's say now it's 100. Well, now we're too heavy. It's supposed to be 66. So what it does is it creates a more, let me reword that. So what it does is it causes these to react and make more products. So when it does that, it actually starts to use up some of the energy. So the extra energy that you just gave it is trying to alleviate that because it doesn't want it. It wants to be balanced. So it shifts to the right and it goes back to being at equilibrium. Now, we're basically out of time, but I'm gonna add something real quick, and then you can ask your question. How would this affect the concentration of N2?
Would it make it like more concentrated?
Try again.
Less?
That's what the homework's gonna ask. So we're shifting right, what does that mean? I'm using these up to make more of this. So both of these will decrease, that will increase. Because you're shifting that way. Questions, thoughts? We're all set. Okay. So we're all set. Do that worksheet here. You only have 6 boxes or six questions. So.
So